I'm going to be walking through a small live demonstration of the current state of our debugging tools for the Spritely Goblins OCAP system. I'm just going to be, don't mind me, I'm copying over some things from another buffer just to import the code that I need to use for this demonstration. So for those that are familiar with E, you may find a lot of this somewhat familiar. A lot of our inspiration for this tool is coming from Causeway, which was E's distributed debugger. I guess the big difference here, besides the fact that this is Scheme that we're working with and not E or JavaScript or something like that, is that because we're in Scheme, we tend to do things, what we say, live, meaning at the REPL while the program's running. So all the debugging we're going to be doing here is going to be happening all while the program is running. We're not going to stop it. We're not going to do anything post-mortem. It's all going to be live. And I guess the other big feature that we want to show off is that we call this a time-traveling debugger, in the sense that we keep historical data about actor behavior, such that while we're debugging, we can kind of travel back in time and check out what the state was at various points in our search for buggy behavior. So the demonstration, or I guess to set this up, this example is we're going to be making a very simple, kind of naive e-commerce platform, and it's going to take place between 3 different vats. And there's some stuff involving inventory and warehousing, there's stuff involving the actual order placement interface, and there's also some money-related stuff. So I'm going to start introducing some actor constructors here. And now, if you don't know Scheme or anything, don't worry too much. The code is not so important for this, but I will just explain and highlight important behavior. Great. So this first actor we're defining is known as the shipper. It's very simple. It accepts in this constructor a list of valid addresses, and there's one message you can send to it. You can ask if it can deliver to a particular address. If the address is in the list, it says, yep, that's fine, returns true, otherwise it returns false. So that's quite simple. The next actor we'll be defining, this is a constructor for a very, very simple and naive payment processor. It is able to take funds from customers and put them into purse. So we're going to be using this for the store to get its money. So we have one method that checks if a customer's purse has enough money in it to make a purchase, and we're able to collect payment with the submit payment method. And again, there's some very Goblin specific and like Scheme code here. Don't worry too much about it if you don't understand what it's exactly what it's doing, because I know we're moving kind of fast here to demonstrate all the debugger features. This next actor constructor is the most complicated one, so I will definitely reiterate, don't worry too much about the code. This is the inventory actor, and when you construct it, it takes some data structure that tells about the inventory that it has. So we have a warehouse, which is just a mapping of product names to how much quantity there is of it, and a prices object, which just maps item names or part names to how much they cost. And so there's a number of methods here. We can get the current quantity of a part in the warehouse. We can restock a part and add quantity to it. We can check if a cart, which contains many parts and quantities, if all of those items are in stock in the given quantity. We can get the total cost of a cart by consulting the price list. And finally, the real state-changing stuff here is that we can pick the items from a cart out of the warehouse, presumably to be shipped to the customer. So that's the scenario we're modeling here. And finally, one more actor constructor. This is kind of our main interface to the whole demo, and it's the store. And the store gets a reference to the inventory actor, the shipper actor, and the payment processor. And it has just one method, place order, given a customer's address, a purse to withdraw money from, and a cart containing what they want to buy. It will do a bunch of stuff. And for brevity here, to not make this way too much code to show in a demo, it's either going to tell you that the order was confirmed or the order was failed, if based on various success or failure criteria. Okay. So let's start building our world. We're going to use 3 vats to do so. This first vat, which we're just calling vat A, is going to contain the inventory and shipper actors. It's going to be kind of like our fulfillment services actor, I guess you'd say. We have a second vat, just for simplicity again, calling it vat B. And vat B is where our store actor is going to live. It's going to be the only actor in that vat. And finally, we have vat C, and that's going to house all of the financial actors. So it's going to house that payment processor, and it's also going to house an actor from our standard library called the simple mint. And for those that are familiar with E, what Christine tells me is our simple mint is actually directly from the E literature. So we're using that to simulate some currency here for this demonstration. Spawn our actors in the vats. So I'm going to start with creating the inventory actor. Again, that lives in vat A. And this is a very Lispy thing here, but all you really need to know is that this is a very sparse warehouse. It only stocks cookies that cost 1 token of currency each, and there are a dozen cookies in stock. Very, very small inventory. The next actor is the shipper. We'll spawn that, and very sparse list of valid addresses. 123 Sesame Street. That is the only address that this store can deliver to. This is the mint, and this one, again, lives in vat C. That's where we keep financial stuff. This is from our standard library. It's able to, basically generate bank accounts that we're going to use for the demonstration. So using the mint, we will generate a new purse for the store with a starting balance of 0 tokens. Fine. We're going to create a payment processor. And again, that's in vat C, and it's going to have access to the store's purse to place customer money into. And finally, we spawn the store, and that's the one that lives in vat B. And again, we give it references to the actors, inventory, shipper, and payment processor. Great. Okay. So I will define one other bit of code, and this is just going to help my demonstration, my one-liners have less text in it. We're going to make a little helper procedure that's going to help us order cookies. We're going to specify the amount of tokens that we want this fake customer to have in their purse, the address that we'll ship to, and the quantity of cookies they want to buy. So the important thing is that we are using the place order method on the store. So this dollar is just another way of one of Goblin's operators for sending a message to an actor. Okay. So now we're going to start to get to some of the good stuff. And I'm going to start introducing these little tools that we have in Goblins. So we take advantage of Guile, the scheme implementation we're using. We take advantage of their extensible REPL tool facility called meta commands. And that's what these little things are that begin with a comma at the REPL that invokes a command. We have a number of custom commands that we use. And that's how all of our development and debugging interfaces are implemented. So this first one is called enter vat. And what it allows us to do is jump into a sub REPL session in the same process still, but it's in the context of vat B. So anything that we evaluate will be done within the context of vat B so that we can do things like directly spawn actors, send messages, all of the things that need a vat context to happen. It's a developer convenience. And enables is using pretty much every other tool that we offer in Goblins. So what I'm going to do now is just show you some error cases to show you that invalid input to the ordering is going to fail. So in this case, we're going to try to do an order with a purse with 12 tokens in it with this invalid address of 456 Sesame Street and with a valid number of cookies. So the only thing that's wrong here is the address. We should get a failure. Okay, order failed, great. And again, for brevity, the error messages are not descriptive of exactly why it failed, just to keep things simple. This is a case where we don't have enough tokens in order to make the purchase. The address is fine. We're ordering 12 cookies, which the inventory has, but we only have 11 tokens, so that should fail too. Cool. And the last error case is not having enough stock in the store to satisfy an order. So we have 13 tokens, which should allow us to buy 13 cookies, but the warehouse only has 12, so that will fail as well. Great. And now we'll show a success case. So we have 12 tokens in the wallet, a valid address, and a valid number of cookies. So we should get order confirmed. We do. That's awesome. So I'm going to introduce kind of the first debugger tool, and we're not actually debugging it, but just to show you what things look like is we have this command called that tree, and what it allows us to do is inspect the causality tree of a particular message. So in this case, if I don't give an argument, it's going to look at the last message that was handled, which is the one right above us here. So if I run that tree, what I see in this output is a bunch of stuff, and if you're not familiar with Goblin's nomenclature and stuff, which I imagine pretty much everyone is not, what this is showing here is on the first line, this is our entry point when we place this order called the order method. And in Goblin's terms, this call with that thing is what we understand as kind of placing a computation into the vat to be run. So we recognize this as kind of like an origin point of things. And you see messages like us creating a purse, checking the cost to see if we can get the cost of what we need to withdraw from the customer's purse, checking if there's enough funds in the purse, et cetera, et cetera. Here's one where we're submitting payment. And importantly, kind of the end result of everything is if all the checks pass, we call the pick method on the inventory. And we say, yes, we did all the checks. I think we can satisfy this order. Please pick everything from the inventory. And which ultimately leads to this message saying that the order was confirmed. So this is a message order tree. And these identifiers here, for those, I imagine a lot of people are familiar with Lamport timestamps. So these are actually a simple Lamport timestamp for ordering and getting some like partial causality order. The happens before relation, for those that are familiar. Okay, so that's kind of neat, but I'm here to show you debugging. So let's get into some problems. So to start with, I'm going to restock the inventory because I just purchased 12 cookies, so now there's not going to be any cookies in the inventory. So right here, okay, there's 12 cookies in the inventory currently. I just checked. I've been using, and not really talking about it, but I've been using this additional fun meta command we have called vat resolve. And basically what it's doing is this code right here is sending an asynchronous message, which in Goblins generates a promise, basically a placeholder for a future value that may come back in time. And what vat resolve is doing is just waiting for the answer to come back and then presenting it to us, or showing us that an error happened if the promise was broken. Okay, so let's set up a scenario that's not going to work right. So the code that I showed you, all these actor constructors, it's quite naive. There's bugs in it, and we're going to focus on one particular bug. So what I want to demonstrate is a race condition. So I'm going to do a little, add another helper procedure here to help to demonstrate this, and it's called double order cookies. And it has the same signature as the first thing. It starts with some number of tokens, an address, and the amount of cookies we want to buy. And what it does is places two orders simultaneously, or one right after the other, and gathers up the results of both to return to us. So Yes, so it'll place 2 orders for the quantity of cookies you ask for. And therein is going to lie some problems. So if we try to double order cookies and we have 24 tokens in our purse with a valid address, and we want to double order a dozen cookies, what we expect to see is that one of these orders is going to be placed because there are 12 cookies in stock, and the second should fail. So let's see if that's what we get. Hint, hint, it's not. Okay. So what we see here is that both orders were confirmed. And of course that's wrong because there were only 12 cookies in stock. So there's a bug. Why did that happen? Maybe let's take a look at the inventory. Let's do a little bit of inspection first before we dig deeper. How many cookies are in stock right now? -12. Great. So we've oversold our inventory. That's if this were a real business, that would be pretty bad. So let's get to debugging. Let's see what's going on. So I'm going to introduce a new command here. It's called vattail. What it does is it just shows in chronological order the last n messages that the current vat that we're focused on here has processed. So let's check out just the last 20 or so, 20 messages here. So this is one way of viewing past events in Goblins. So it is limited to just showing events in a particular vat and in chronological order. So it's just a linear list. It's handy, but what it does not show us how messages relate to one another, and we're going to get into that. But what it does let us do is I see like right here, I see this list is what we got as a result, the double order confirmed. And this message here, 371, is actually the terminal point of this double order. Event 371 is actually the terminal point of resolving this the promise that's generated by the double order. So this would be a particularly good place to start debugging. So we have a handy command just called vat-debug, and you can give it an event identifier. And what it's going to do is launch yet another sub-REPL, indicated by the 2 here. But this sub-REPL has access to debugging tools in the context of event 371. So one of the handy things we can do now is we can get the distributed equivalent of a backtrace. So this is much like a backtrace in a sequential debugger that most of us are used to, but this actually goes through the direct causes of asynchronous messages. So if I run vat trace, what I see here on the bottom is the last message that happened. So this is where we started in our debugger, this 371, the resolution of a promise. And if I go up, each event as I go up is the direct predecessor to the following event. So this is a causal relationship here. And as we go up, one thing I see here is that, here's the call to pick the inventory. And here is the resolution of that, where we're passing back hash t, which in Scheme means it's the Boolean true value. So, the pick shouldn't have happened, right? The inventory, there was no way that there, at that point, there was likely not inventory in stock to do this. So I'm suspicious of that area of this trace here. So let's look back and see if we can figure out what was going on. So we have another handy command. We have a series of things. So much like in a sequential debugger, you can go up and down the call stack and inspect local variable values or whatever your particular debugger can do. We can also move up and down this asynchronous trace, and in doing so, we can go into contexts where we're actually changing vats. So we can look into the state of vat A or the state of vat B or vat C. So vat A is where all the inventory stuff happens. So if I jump into an event that happened in vat A, I think we can start to figure out what's happening. So I'm going to go into 343 here. And as this states, we are now in the context of vat A, in the context of this particular event. And this is where the time traveling part of our time traveling debugger comes into play. So we have an actor reference assigned to the variable inventory. Well, with this new vat peak command, we can send a message to this actor at the time of event 343. So what we can do here is ask it, how many cookies were in inventory at this time? Okay, we see that it's negative 12. So the state change, the bad state change we're looking for has already happened. So as I said, we can go up and down the distributed call stack here. So if I go up a frame with the vat up command, I am now in the previous event, 342, and it happens to be at the point at which we actually called the pick method on inventory. So if I check the state of the inventory at that point, what I see is that the inventory for cookies was 0. So pretty cool. This is the time travel part. This is not the current state of the inventory. The current state is negative 12. But thanks to Goblins transactional state management, we take snapshots, and we're able to look back at previous snapshots and see things. Cool. So we know between events 342 and 343 that we decremented the quantity too far. We shouldn't have done it. It was already 0. We should have stopped there. Great. So this is an example of a pretty classic, or a simple example of a classic time of check to time of use bug in which we had a race condition where we had done pre-flight checks on both orders, but we failed at the actual time of modifying the state and actually placing and fulfilling orders to verify that things are still in the state we had expected them to be. So I'm going to exit the debugger, and I'm going to get back to the top level Guile scheme REPL, and we're going to fix the bug. This is the original implementation of the inventory actor, and this in-stock check happens here, and that's great. It does accurately check that the cart's in stock at that time, but when we go to pick, it doesn't check at that point. It just assumes that everything's there, and it starts decrementing the value of something right there. So that's the bug. What we need to do is introduce a check. So I'm going to just copy paste from our other oven, to use cooking show terminology. The fixed version of this code has a nice handy new check stock procedure that we use in the in-stock method, and that we also use prior to picking. So now in the pick method, we're actually going to do the check. Because of the VAT model of computation, this pick method is happening synchronously. So now we don't have to worry about a race condition. We can actually check the stock, ensure that yes, things are as we expect. We can actually pick this, and if not, we can throw an exception and just say there's insufficient inventory. Okay, great. So all that's left to do now is verify that this has actually worked. So I've updated the actor constructor. That's what I just did there. I've redefined it. So there's new behavior, and what I need to do now is spawn a new inventory actor using our updated version of the inventory constructor. So we have that hopefully bug-free behavior. And I'm going to also respawn the store with a reference to that actor that has the hopefully fixed behavior. If I go back into vat B, I can attempt to do the double order again. And what I should see is an error message now that we're raising one. Great. Okay. So now we see that the promise was broken. When we tried to place the second order, there was insufficient inventory. So the bug has been fixed. And not only has the bug been fixed, we fixed it without having to stop the program. So we were able to inspect past program state, fix the bug, test the fix, all within the REPL in a pretty convenient manner, which I think is pretty neat. So that's the end of this debugger section, but what I want to leave you all with is one last tool that we wrote that we think is pretty neat, that allows you to view in a graphical manner the causality of a particular group of events, related events. So I'm going to restock the cookies since that last run brought it down to 0. And I'm going to try to do the purchase again, just a single one. Okay, that went through. And now I'm going to run vat graph. And I'm going to scroll up. And what we have here, and it doesn't all quite fit on one page since I had to shrink my window, but what we have here is a graphical representation as a Lamport diagram of the whole process that we run, starting with the, like I said, the call with vat, which is the typical origin point of something in Goblins, minting a new purse and doing all the pre-flight checks and then eventually placing an order. So we keep a lot of information here to present to users in all sorts of different ways, and I think this is a particularly nice way to visualize message order and get an idea for what's happening in a system.